We have learned how to add two matrices of the same size, and we've learned how to multiply matrices by scalars. Where things get really interesting is when we start multiplying matrices by matrices. And over the next 3 videos, we're going to develop a definition of matrix multiplication, and we're going to look at that definition from several different points of view. And I hope that even people who've met this definition of matrix multiplication before are going to learn something new from this. So we'll begin with the definition of matrix multiplication. We take an m by n matrix A, and I'm going to write that by saying that its ij entry is this, lowercase a subscript ij, and we'll take an n by p matrix B, whose ij entry is bij. And in that case, the matrix product A times B is defined to be the m by p matrix, whose ij entry is given by this formula. So before we investigate this definition any further, let's just highlight one thing, which was that it was really important that the number of columns in A must be equal to the number of rows in B. In other words, those two n's really are supposed to be the same n. So the number of rows in A the number of columns in A must be the same as the number of rows in B for the matrix product A times B to be defined. Otherwise, we simply do not define that matrix product. So in this case, the result, the product matrix A times B, will be m by p. In other words, it will have the same number of rows that A did and the same number of columns that B did. Okay, let's look at this formula a little bit more carefully, and let's look which elements of the matrix A, which entries from the matrix A appear in the sum defining the ij entry of A times B. So the entries from A which appear are here. And if we're looking at the ij entry, then the entries appearing in this sum are ai1, ai2, ai3, up to ain. In other words, the entries from A which appear in the sum defining the ij entry are the entries from the ith row of A. Okay, so now let's think about which entries from B appear in this sum defining the ij entry of A times B. So those entries are B1j and B2j and B3j all the way up to Bnj. And if you think which entries those are in the matrix B, well, those are the entries from the jth column of B. So in order to get the ij entry of the matrix product A times B, what we're doing then is looking at the ith row of A and the jth column of B, multiplying together the corresponding entries and adding up the result. And in practice, that's an easier way to think about what matrix multiplication actually does, and it enables us to actually work out some examples. So we're going to spend the rest of this video working out some examples of matrix multiplications using this formula. Okay, so let's begin with the example at the bottom here. We're going to multiply together two 2 by 2 matrices. And let's think, first of all, before we do any multiplication, let's think why this is allowed. So the first matrix here is 2 by 2. So let's call the first matrix A and the second matrix B. And the second matrix B is also 2 by 2. So we're allowed to do this matrix multiplication because the number of columns in A is the same as the number of rows in B. Right? The number of columns in A, that thing, is the same as the number of rows in B, which is that thing. And so the answer, the result matrix, whatever it is, will have the same number of rows that A did and the same number of columns that B did. So the result will be again 2 by 2. And how do we work it out? Well, let's think first of all about the 1, 1 entry of AB. So the 1, 1 entry, we get it by multiplying the first row of A, so that's this stuff here, with the first column of B, and that's this stuff here. And the way we do it is we multiply together the corresponding entries and then add up the results. So what we will have is, let's just make this a bit wider, we will have A times E plus B times G. That will be the 1, 1 entry of AB. So now let's look at the other entry in the first row of the product A times B. This time we're going to multiply the first row of A and the second column of B. So this time we'll have A times F plus B times H. Okay, second row of AB. This time we'll be multiplying the second row of A with columns from B. So the 2, 1 entry, so the entry in row 2 and column 1 of A times B, we'll get that by multiplying row 2 of A by column 1 of B. So C, E plus D, G. That will be the 2, 1 entry, and if we want the 2, 2 entry, then we will multiply the second row of A and the second column of B. So we'll get CF plus DH. Okay, so there's a general expression for the product of any two 2x2 matrices. So let's try another example now. Let's look at this second matrix product. I'm going to call this A, and what we're multiplying the 3x3 matrix A into is a 3x1 column vector. And often when we write column vectors, we give them lowercase letters, and usually if I'm typesetting one of these, I'll give it a bold lowercase entry, lowercase letter. So I'm going to write it as U with an underline instead of doing a bold U like this. Okay, so what are we doing? We're multiplying a 3x3 matrix into a 3x1 matrix. So first of all, we're allowed to do that because the number of columns in A, which is 3, is the same as the number of rows in U, which is 3. So we're allowed to do this, and the result will have the same number of rows as A, so it will have 3 rows, and the same number of columns as U, so it'll have 1 column. So the answer will be 3x1. So another column vector, in other words, another 3x1 column vector. And let's work out what the entries are going to be. So if we want to work out the 1, 1 entry, then we multiply the first row of A into the first column of U. So we'll get 1 times X plus 2 times Y plus 3 times Z. Okay, and if we want the 2, 1 entry of A times U, we'll multiply the second row of A into the first column of U. So we'll get 4 times X plus 5 times Y plus 6 times Z. And finally, to get the 3, 1 entry of the matrix product, we'll multiply row 3 of A into column 1 of U. So of course we get 7 X's and 8 Y's and 9 Z's. Okay, so that's how our matrix multiplication works, and because it's so important, let's try and do a few more examples. So I've written at the top here the general definition of what matrix multiplication looks like, the general formula for the product of two matrices when that product is defined, and we're going to work out a few examples of doing this. So let's see whether these examples actually fit the definition first of all. So each time we're going to work out whether we have a really legitimate matrix multiplication or not. So let's see what we've got here. We have here a 3x2 matrix. It's got 3 rows and 2 columns. And here we have a 2x1 matrix. So 2 rows and 1 column. So we are allowed to do this matrix multiplication. This is okay because the number of columns in the first matrix is the same as the number of rows in the second matrix. They're both 2. So the result will then be a 3x1 matrix. Okay, what's a 3x1 matrix? It's got 3 rows and 1 column. So it is a column vector, a height 3 column vector. So let's do this. To get the entries, well, the 1, 1 entry will be obtained by multiplying the first row of the first matrix into the first column of the second matrix. So we'll multiply 1 times 7 plus 2 times 8. And the 2, 1 entry of our product would be obtained by multiplying the second row of the first matrix into the first column of the next matrix. So this time we'd have 3 times 7 plus 4 times 8. And that's more than my mental arithmetic can cope with at the moment, so you're going to have to work out the exact number yourself if you want to know exactly what it would be. Finally, the 3, 1 entry of the product would be obtained by taking the third row of the first matrix, so 5, 6, and multiplying it into the first column of the second matrix. So we'll get 5 times 7 plus 6 times 8. Okay, this one really is above my pay grade. You will have to ask a professor if you want to know the answer to that. Okay, let's do another one where hopefully the arithmetic's a little bit easier. So we'll move on to our second example here, where we have a 1 by 2 row vector. So a 1 by 2 vector. Okay. And I'm going to multiply this into a 2 by 3 matrix. Okay, this second one has 2 rows and 3 columns, so it is 2 by 3. So we have a 1 by 2 matrix and a 2 by 3 matrix, and we are allowed to multiply those things because the number of columns in the first of them, there are 2 columns in the first of one, is the same as the number of rows in the second one. And the result will be 1 by 3. In other words, it will be a 1 by 3 row vector. So let's work out some of the entries. The 1, 1 entry will be obtained by multiplying the first row of our first vector, the first matrix, into the first column of the second matrix. So I'll have 1 times 0 plus 2 times 1. So that is 2. Even I can work that one out. Okay, the 1, 2 entry in our product will be the first row of the first matrix times the second column of the second matrix. So that's 1 times 2 plus 2 times 0, which is 1. And finally, the 1, 3 entry in the product would be obtained by multiplying the first row of the first matrix by the third column of the second matrix. That's 1 times 0 plus 2 times 1. That is 2. Okay, a couple more, so some slightly unlikely looking matrix multiplications. But here we have a 1 by 3 matrix times a 3 by 1 matrix. Again, this is a legitimate matrix multiplication because you are trying to multiply something with 3 columns into something with 3 rows, so that's okay. And the result will be, a 1 by 1 matrix. And very commonly, we'll actually identify a 1 by 1 matrix with a number. So that's the only circumstance in which we'll ever identify a matrix with a number. But usually, in fact, most of the time, when we've got a 1 by 1 matrix, we'll just think of that as the number, which is its entry. So here we would have 1 times 1 plus 2 times 1 plus 3 times 1, which is 1 plus 2 plus 3, which is 6. So this, if you've ever seen dot products before, this is a bit like a dot product where the answer is actually a number. Okay, right, last example then. So last example of doing a matrix multiplication. What have we got here? We've got a 2 by 1 column vector and a 1 by 2 row vector. Again, the number of columns in the first thing is the same as the number of rows in the second thing. So it's okay for us to do this, and the result will be 2 by 2. Okay, so we'll work it out. What do we get? The 1, 1 entry will be obtained by multiplying the first row of the first matrix into the first column of the second matrix, so that's 1 times 3. The 1, 2 entry in the product would be the first row of the first matrix times the second column of the second matrix, so that's 1 times 4, which is 4. And the 2, 1 entry would be the second row of the first matrix times the first column of the second matrix, so that will be 2 times 3, which is 6, and then the final entry will be 2 times 4, which is 8. So you can see what we've got there is we had a matrix where the first row was just 1 times 3, 4, and the second row was 2 times 3, 4. And equally, you can think about this by columns as well. The first column was 3 times 1, 2, and the second column was 4 times 1, 2. Anyway, what we got there was 3, 4, 6, 8, however we worked it out. So let's finally, just before I end this, let's look at an example which wouldn't be okay. So if we had something like 1, 2, and you tried to multiply this into 3, 4, 5, okay, what happens there? Well, there you have a 2 by 1 matrix, and you have a 1 by 3 matrix, so this one would be okay. You could work this out. The result will be 1 times 3. But what if we did something different? So what if instead we tried to get rid of this and said, what if I had a 2 by 2 matrix? So if I had something like 1, 2, 3, 4, like this. So this time we have a 2 by 1 matrix, which we're trying to multiply into a 2 by 2 matrix. All right, this one is not allowed, right? This is not a legitimate matrix multiplication because the dimensions don't match up. So if you want to multiply 2 matrices, the number of columns in the first one must be the same as the number of rows in the second one. That doesn't apply here, so you're not allowed to multiply them.